Hello, in this video I'm going to look at integrals that involve trigonometric functions. So basically at this point you've probably already looked at integrating such things as cosine squared, sine squared, secant cubed, um, maybe tangent squared, yeah. But let's go ahead and look at ones of which that we have products, okay? So we first start by looking at what happens when you have one of the powers that could either be even or odd, and what would we do? Now, one thing that you may need to consider is that you will be using a lot of use of the fundamental identity, sine squared plus cosine squared, theta equals to 1, and then also tangent squared theta plus 1 equals to secant squared theta. Now that's not the only one that you would probably be using. Such things as, like sine squared theta equals to 1 minus cosine 2 theta divided by 2. And then similarly, these sine squared theta equals to 1 plus cosine 2 theta divided by 2. Now, you actually have that there are some other, identities that, could be useful, but, maybe we'll see, some of those along the way. So let's look at one of which that involves the integral of sine squared x, and then we have cosine to the fifth x, and this is going to be dx. So here we have to kind of consider what's one thing that we can do to rewrite this, for example. Because we know that sine squared is 1 minus cosine squared, but that's not really going to help us in either case. So what we can do probably is, what if we were to say, for example, remove a sine. Okay, so if we remove a sine, we could think, will that help us? And it may, but then we have to consider what would be our u. So it looks that, for example, that I need to work with cosine at the moment, because I know that if I go ahead and I say, well, I have the integral, and that's going to be sine squared x, well, I can rewrite this as cosine to the fourth x, and then have a cosine of x. The other thing of which that we'll know is that, for example, that the cosine to the fourth x, it's really 1 minus sine squared in a way. But how? We'll see. So notice that this is going to be cosine squared x, and that's squared. And then you have a cosine x on the outside. Now, notice that from there, you can actually say that 1 minus sine squared x is actually going to be substituted. So we have sine squared x multiplied by 1 minus sine squared x, and that's all going to be squared. And this is times cosine of x dx. From there, we need to use possibly a u substitution. So let's go ahead and choose our u to be sine of x, and then du will be cosine of x dx. Okay, so what that does is it changes the integral into the following. So here we have u squared multiplied by 1 minus u squared squared, and then we have du. Okay, so that's going to be the integral of u squared times 1 minus 2u squared plus u to the fourth, and then that's going to be du. From there, we just distribute, so we have the integral of u squared minus 2u to the fourth, and then you have plus u to the sixth, and then of course, at this point, it becomes clear that we just need to take the antiderivative by adding a power back. So we have u to the third divided by 3 minus, well, it's going to be minus 2/5 u to the fifth power and then plus u to the 6th, actually it's 7, divided by 7, and then we do plus c. So from there, you just need to substitute the cosine, not cosine, but the sine function. So that's going to be sine cubed x divided by 3 minus 2/5 sine 5x plus sine to the 7th x divided by 7, and then plus c. Now, of course, if you differentiate this, it's going to give you back the integrand function. But this wasn't the only way that we could do this problem, for example, because I could have probably, changed the sine squared again as cosine, but notice that it wouldn't really help necessarily, because then you'll end up with cosine to the 7th. Then it becomes a question, well, what is cosine to the 7th? How do you solve that? And probably, off the top of my head, probably by parts, maybe, or some type of reduction formula that you've seen in class. So another example that we can look at is the following. So let's say that we have an example of which has sine squared x, and then we have cosine squared x dx. Now this is where one of those identities comes into play, because for example, 2 sine theta cosine theta is equal to sine 2 theta. Okay, so looking at that expression right here, that's actually well, that's actually basically sine of x cosine of x, and that's going to be squared. But basically that's going to be 1/2 sine 2 theta, and it's going to be squared. So what happens is that the integral is actually going to be 1/4, and then you have sine squared 2 theta d theta. So from there, we just need to figure out like what we can do to rewrite that integral. Now, luckily, we have a reduction formula that says that you can say 1/4 times the integral of 1 minus cosine of 4 theta over 2, and then you have d theta. Now, what that means is that basically you can rewrite it as 1/8 integral of 1 minus cosine of 4 theta, and then of course it's just going to be d theta. Okay, well from there all that we need to do is just integrate each term by term. So that's going to give us 1/8. Oh, I just realized I'm using thetas, but it's okay. Yeah, let me, I mean, we could change it. Yeah, I guess, yeah. Let's go ahead and change it to theta, or to x, right? So that way there's consistency. So you have x and then dx, and then you have theta and d theta. Oh, it needs to be a little closer. Yeah, 4x. And then over here, we're just going to change that to a 4x, right? Okay, so I mean, it's really not that important in a way, because as long as we know what we're talking about. But I guess like if we were going to use a limit of integration, then of course that's where we might get into some trouble. Okay, so that's sine 2x. Okay, now here, yeah, okay, so here we have 1/8 x minus, well, in this case, that's going to be minus 1 over 32 sine of 4x, and let's see, yeah, minus 1 over 32 sine 4x, and then plus c. Okay, so this should be it in either case. Now, I don't know if, like, maybe if you would have substituted 1 minus cosine squared, that would have been a good idea, because then you would be integrating cosine to the fourth, of which it would bring you back to the same question as to what's the integral going to be. But another idea that you could probably implement is substituting the double angle for each one respectively. But if you do that, then that means that basically it kind of leads you to the same route, essentially. But that's something to think about, is like, just taking those different approaches, for example. Now keep in mind that there are reduction formulas for sine squared, respectively, that you've seen in class before. So, and of course you can use integration by parts as well, too. So that's, just letting you know that there's different methods that can be implemented that you've probably have seen already. Okay, now let's say that we had the following example, of which that we have an integral that involves a secant function, and we'll stick with x's for the we'll stick with an x for the variable. So we have tangent of x dx. Now the question becomes, okay, well, how am I going to basically solve this? Well, you have to basically peel out one of the functions. So you have secant cubed can be rewritten as secant squared x, and then you have secant of x, and then you have tangent of x dx. Okay, now it looks that basically I can go ahead and implement a u sub now, because note that, for example, if I let u equal to secant of x, then I know that du is equal to the secant of x times the tangent of x dx, which in that case means that all of this reduces very nicely. So we have the integral of u squared, and then you have du, which this is going to be u to the third divided by 3, and then plus c. However, we know that basically this is going to be well, it's going to be it's going to be secant cubed, basically. Yeah, so you have secant cubed x over 3, and let's see, then that's going to be plus c. Okay. Now, if you differentiate it, of course, it just brings you back to the original function. And, you just have to use chain rule, essentially. Now, that one was not actually too bad at all, because essentially we just needed to peel out one of the secant functions. Very similar to the very first example, how you had to peel out one of the functions, basically, in order to use a u sub. Well, yeah, we did peel out a cosine, basically, from the odd function. And that's one pattern that you can kind of use in either case as it relates to how do you solve trigonometric integrals. You basically just have to peel out one of the functions so that it's now what you can say integrable in either case. So the next one is secant to the fourth x times tangent. So let's say that we're looking at an example of which that you have the integral of tangent to the fifth x, and then you have secant to the fourth x, and this is going to be dx. So the question becomes, how do you solve this one? Well, basically the way of which that you should solve this is by basically using that secant to the fourth can be rewritten. So you have tangent to the fifth x, then you have secant squared x, and then you have secant squared x. So essentially we have the integral of tangent to the fifth x times, well, notice that that's just going to be tangent squared x plus 1 multiplied by secant of x. But that's squared, right? And that's dx. So check this out. This means that u can be tangent of x, which means that du is secant squared x dx. But we already have that, essentially. That's going to be for this one. So du is going to be this part, which means that we have the integral of u to the fifth times, well, that's going to be u squared plus 1 times du, which at that point it kind of becomes clear that, if you distribute, you have the integral of u to the seventh plus u to the fifth, and then from there you know that you just have to integrate each one, of which basically it gives you 1/8 tangent 8x plus 1/5 tangent, not 1/5 actually, right? It's supposed to be tangent to the 6th power, so that's going to be a 6 actually in the denominator. So tangent to the 6th x, and then plus c. And then that would be it. Of course, if you differentiate, it's going to bring you back to the same equation that you were integrating, or the same function that you were integrating. But here, it didn't require as much in either case, because here, I had to use that my u was eventually going to be tangent. So in that regard, I had to think about, when I differentiate, what's going to be my u. And I I placed it over here on purpose, basically, so that we could use that, once we pick our u, that this would go away as it gets substituted with du, essentially. Now, if I wanted to integrate something of, a higher power, for example, such as like secant to the 6th x dx, well, I can try to integrate this basically by coming up with some ideas. By, let's say, for example, we go ahead and we rewrite it as secant to the 4th x times secant squared x dx. But now, at this point, you should see where I'm going with this, that you can actually just substitute the identity tangent squared x plus 1 squared, and then you have secant of x squared dx, which basically means that this is more or less just a repeat of what you've already seen, essentially. So with that, this means that your solution, if you were going to solve for the integral of secant 6x, basically is going to be 1/5 tangent to the 5th x plus 2/3 tangent cubed x, and then you have plus tangent, and then plus c. So this would be the solution, this would be the solution to how do you find the antiderivative of secant to the 6th x. Now, in actuality though, like if you wanted to take much more complex methods, basically what you could probably do is, where you say that you broke it up as secant to the 4th x and then secant squared x. Basically, what we could do, for example, is just label this as dv and this as your u. Yeah. So essentially, when we do that, you're using integration by parts. Now, integration by parts is actually going to get you the same answer. Well, it's going to get you an answer, but how you find it, like in presentation wise, it's not going to look exactly the same because of the fact that you're using a different approach. But once you kind of like work out the solution in terms of like differentiating it or even rewriting it, you'll see that it's essentially the same thing as what we have right here. So in that regard, you can apply integration by parts for a question like this. But if you are going to go the route of using integration by parts, the u v minus the integral of v to u, and this is our integral of u dv. If you're going to use this route, then I don't know, I feel like maybe it might be just better to just use a formula that you can derive for secant to the power nx dx by the use of integration by parts. Because there is what we call a reduction formula for secant to the nx. Basically, it requires that you'll use integration by parts to derive the formula. But in either case, this is something, again, that you've probably have seen in class. So like I'll just put, use integration by parts to derive. Okay. Otherwise, it's something that you're probably just referring to, like a handout that you received in class.